Hello and welcome back to the Raspberry Pi coding channel. This is the second video in my new series on humans versus AI, where we're covering off reinforcement learning and creating a basic game of increasing complexity. At this point, we've just been through some theory and laid out what this series is all about. So this is the video where we're going to actually get into the coding. And by the end of this video, we're going to create a very basic game window with a grid that we can see rendered. We're also going to install our dependencies, so we're basically ready to go in the following videos. Okay, quick reminder that I have a Patreon account if you wish to contribute. No pressure at all, no expectation, but it's very kind. Some people like to contribute if you do. It's very much appreciated. And as a thank you, you'll have access to the code that you see in the videos, so you can copy and paste it if you like. And you'll also have early access to videos, since I tend to release videos every few days. So if you want early access, you can get it that way as well. Okay, over to my terminal. That's always where we start these things. So I've got a folder here, and I'll show you the content of it, called video, and it's got 4 files in it, and you can completely ignore that because they are just the files that I've split out to try to make explaining what I'm doing easier. So 1.py contains the code, the full code for this in quotes lesson, and then 10, 11, and 12 are basically that code broken out into sections to help explain it. So those you don't have to worry about. In fact, if you wish to code along and do this yourself, I would call your file main.py, main.py. Okay, so that's the first thing to note. Secondly, I use WSL2 on my Windows laptop, which is what I'm using now, which is a very specific way of working, but you don't have to do it that way. I'm using pure Python. I'm using Arcade. So long as you have an OpenGL compatible machine, which by the way, a Raspberry Pi isn't, so we won't be doing the rendering on a Raspberry Pi, then you're good to go. The Raspberry Pi part, as I said in the previous video, will come later on. We won't be doing the rendering and we won't be doing the initial training on a Raspberry Pi. Anyway, keep to time, I'm going to use pipenv as my virtual environment library. You will need to create a virtual environment for your Python code. If you don't, you must. This is standard practice, and I use pipenv to do so. It encapsulates your dependencies and stops you polluting your dependency space of your Python installed version of Python, which can cause all sorts of problems for your operating system. So we don't want to do that. So to do so with pipenv, then, I'm going to do pipenv shell. Actually, I'm going to use shell. The shell command will create a pipenv virtual environment and at the same time enter that virtual environment for me. So I will do that. Okay, so that's installed our virtual environment on my computer. Now it takes its name from the folder. So my folder is called video. So my virtual environment in pipenv is also called video, which you can see by the name here in parentheses on the left. And it's also worth saying that I use Python 10 at the moment. So if you type Python --version, you'll get the version of Python you're using. pipenv will take your default interpreter and apply it to your virtual environment if you don't tell it otherwise. And since my computer has Python 10 on it, my Python version in my virtual environments called video also uses Python 3.10. Okay, with that done then, the next thing we need to do is we need to install a dependency, which I will do using pipenv install arcade. Arcade being the game library that we're going to be using for this project. So it's nice and simple and nice and quick. Next thing I'm going to do is have a look at the pip file that has been generated using cat, which is the command line, a nice command line way of looking inside a text file. And you can see in here, it shows us that we're using Python 3.10 down here at the bottom of this output. And arcade is a dependency. Theoretically, you should pin your dependencies. Not theoretically, actually, you absolutely should pin your dependencies. The asterisk means that it is the latest version at all times, which can cause you problems in production environments, so best not to do that. But for this project and this purpose, it's absolutely fine to grab the latest version of Arcade at the moment, so that's what I've done there. So there we go, we've got a virtual environment called video. At least I've got a virtual environment called video inside my video folder. I've got a load of files that we can ignore that I've already mentioned, and I've got 2 pip file artifact files which are associated with the virtual environment, which you can also at the moment ignore. So I'm going to go into Visual Studio Code now to begin the code part of this video. To do so in WSL2, you can type code and then you can use a period to go into the current directory, which is what I'm going to do. You don't have to use VS Code, but you can use whatever IDE you prefer. Okay, so here we are with the code. The first thing we want to do before we get into explaining what's happening here is we want to make sure that our IDE is using the virtual environment that we've just created. So we need to select our interpreter. So in Visual Studio Code, if you're using what I'm using, if you press Ctrl-Shift-P, you are then able to select interpreter up here, and I can then click video, and that gives me my video virtual environment. So you'll need to do the same if you're using VS Code. Right, that means that VS Code knows about my import of Arcade, and it knows we're using Python 3.10, and not just that we're using it, but in fact, when I run the code, it'll be using that version of Python, that particular executable that's located within my virtual environment. Okay, let's go through the code then. Here we go. So this has been made about as simple as I could make it to explain what Arcade does. So first off, we import Arcade, pretty standard stuff. We've then got some constants which won't change throughout the game, so I've made them constant: screen width, screen height, and screen title. Unsurprisingly, these are the width and height of the window we're going to create, and we'll talk about what happens here in just a minute. We've then got the game app class, which I'll talk about in a sec. We'll come back to that. That's very important. That's how Arcade works. That's how we use Arcade. And then down here, we've got really the entry point. Pretty standard syntax for Python, so I won't go into it too much. We've got the if statement that checks this is a standalone instance of main. If it is, it runs it. If you don't know what this is, look into it. This is a very standard pattern, but this is the entry point. Basically, when I click run, main is going to get run. Main is a function. The name doesn't really matter. It could have been Bob, as long as they're the same. And it would then create, it would instantiate, so it would create an instance of this game app class, which I'm going to talk about in just a second. And it then runs Arcade. Now, the Arcade being the library. So run is what's going to start the game loop. It's going to start it running every frame, going round and round and round, trying to render and update the game state. So this is what kicks it off, basically. So you've got instantiation of the class and then kicks off the actual rendering pipeline. So let's look at how we get into that rendering pipeline. We get access to Arcade by creating a class, and I've called it game app, but like I said, it could be any name. And we're going to inherit a parent class called Arcade Window to create our window. So game app is a child of Arcade Window in this case. And we're going to initialize the window. And you can see I'm using screen width, screen height, and screen title. And by doing so, that's actually all we actually need. I could delete all of that, and it would create a window on the screen of proportions 1200 by 1200 pixels with a screen title of basic environment. And what Arcade does is it'll create a rendering loop, and we can intercept, or we can tap into that loop using two of its methods that we inherit here: on update and on draw. These run one after the other, and they run with every frame of the rendering engine. So we've got on update having a print statement of update, and on draw having a print statement of draw. I've got self.clear in here because that's a standard practice that has to precede any frame, because you have to clear it to do another draw. We don't actually need that here. I've just left it in this file, but later on it'll be useful when we do start rendering. So that's about as simple as I can make it. You've got Arcade imported, some constants, you've got the class being instantiated down here, and then initializing the parent class to create a window. So you've got basically at this point a window, and then we're going to intercept these methods. Intercept's not really the right word. We're going to make use of the parent class's methods to see what's happening. Okay, so let's run the code. Try and keep these videos to 15 minutes or as close as possible. So there we go. We've got the window 1200 by 1200. I'm going to stop it, and you'll see it's printing update, draw, update, draw, update, draw as quickly as it can. It's actually doing it in that order. It starts with update, so that's where you update your game state, and then draw is where you actually draw your features and your artifacts in your window. Okay, it's about as simple as I could make it. So hopefully that's clear and how we get the basics of Arcade sorted. So we go on to the next file. So what I'm doing in this one, the only thing that's changing, is I'm going to render the frames per second on the screen. So the first thing I've added is FPS variable, which I'm setting to 0 for no particular reason. I'm just giving it a value. And then inside the onDraw method, I'm actually going to call a function, which I've written below, called drawFPS. And in the onUpdate method, which, as you know, runs just before onDraw, I'm going to calculate the frames per second. And we're going to use delta time. And delta time is provided to us through the method onUpdate, which comes from the arcade library. Delta time is the amount of time that has occurred between frames. This is important, and we'll talk about this later, but we need to make sure we keep a tab on the actual time that's passing so that the game's state and the game itself can be based on real time and not based on frame rate. Otherwise, the game's logic will slow down if the frame rate slows down, which we don't want. But we'll worry about that later. For now, we've calculated the FPS, which is 1 over delta time, as part of the update cycle. It's a great use of the onUpdate method. And then in Draw, we're drawing using the drawFPS class. Inside drawFPS, we're making use of an arcade library method called drawText. I should mention, it's worth making note of the fact that this is not a computationally efficient thing to be doing, but it works, and for now it's absolutely fine. We're using an F string to plot out the frames per second, using the variable FPS, which is passed through to the method, and then we're just setting its location, 10 pixels from the left, screen height minus 20 from the top, basically, 20 from the top, giving it a color orange and a font size of 14. So we're just leveraging the arcade library to render text to the screen every frame, which is what is happening here. So in every frame, we'll get the FPS drawn. Everything else is the same entry point. All we're doing is creating a function and tapping into the onDraw and the onUpdate methods as before and actually doing something with them now. So if I press play, we should now see, instead of print statements in the terminal, we've got the frames per second in the top left-hand corner, as said, updating every frame, in this case every 60th of a second, in orange. Great. So that's that. And the last thing we're going to do in this video is we're going to render a grid. So everything else is the same that I've just been through, but we're going to render a grid, and so I've created 2 new constants. One is grid size and one is tile size. Grid size gives you the number of grid tiles in the X and Y dimensions in this case. And we'll change this later to be X and Y independent, but for now that's saying it's going to be square 50 by 50 tiles or cells. Tile size is a number of pixels for each of these, and you'll notice the maths works. 50 times 24, we've got 1200 pixels to play with. 50 times 24 equals 1200, so we've got the right dimensions. Okay, so we're going to basically the grid cells are going to fill the window. The only other thing that's changed then is this. We've added, or I've added, I suppose, a nested loop where we go across the rows and the columns and we take a position based on the increment of the loop and the tile size, which we've defined above in pixels, 24 pixels, and we use the arcade draw rectangle method to draw the artifact on the screen, one rectangle at a time. It's highly inefficient. And using the X and Y positions, essentially, to create those artifacts. And the color is dim gray. Arcade has quite an extensive color palette, which you can tap into quite easily. And that's it, that's all that's changed. So if we run this, we should see, a grid appear on our window. Okay, great, but what has happened to our frames per second? Now, the first thing I'll say is I'm not using my dedicated GPU for this. I'm using the built-in GPU on purpose, so that if there's inefficiencies, I get to see them. And you can see there's an inefficiency here. We're drawing 50 by 50 rectangles, or squares in this case, that are overlapping, of course, because they're being drawn over each other a little bit. And it's doing it every frame. And it's not computationally efficient. So this is why we're struggling with frames per second. And this is no good. So it's an excellent example of how we have to be a little bit careful, even if we're trying to create the most basic environments, to make sure that it is at least reasonably optimal. Otherwise, it causes problems down the road when we start writing our machine learning pipeline. So this needs to change. And in the next video, we'll look at how we do that in arcade, and not just in arcade, but it is a general pattern. We're going to do something that's quite common in computer game making, which is to turn this into a rendered feature, into a texture basically, and we'll render that texture in each frame instead of calculating the positions within each frame. So we're going to change that in the next video. Anyway, that's it for today in this video. I hope you found it useful. I hope you've managed to create your environment like I have, and we've started our journey in creating a game environment for our reinforcement learning model. In the next video, we'll create a more efficient rendering process, and we'll continue our journey onwards. Thanks for watching, and see you in video 3.